Hello class, and welcome back. It's been a couple days since we've done a video. Today we're going to be talking about even-odd functions and how integrals are affected by even-odd functions and maybe some of the properties. Let's review first what an even and an odd function is. If you remember, very basic even function, f of x equals x squared. And if you remember f of x equals x squared, the reason why it's an even function is because for every x, there's a y, and for every negative x, there's that same value of y. So you know what x squared looks like. It's a parabola going through the origin here like this. And there is a point we can say that this number is, say, 2. And there is 4 on here. Right, so the point 2, 4. Since it is an even function, that means there's a point negative 2, 4 on here as well. You may remember the symmetry, that the symmetry is about this axis right here, the y-axis. So that's an even function. How about an odd function? Well, an odd function, well, just to do the most basic, f of x equals x cubed. That states basically for every x, there's a y. For every negative x, there's a negative y. That opposite kind of field. So if you think of what x cubed may look like, you have something like this. And if we said, okay, well then let's make this 2. If this is 2, 2 cubed is 8. This would be the point 2, 8. And if it's an odd function, and that's only true if it's an odd function, that means we have a negative 2, negative 8. You may remember how that is symmetric. The line y equals x. That's symmetry. Alright, this is an odd function. So let's talk about some integrals involving even and odd functions. So let's look at an even function. I don't care what the function is. I mean, I will, let's stick with x squared, since we're already there. F of x equals x squared. If I were to graph x squared again, here we go, and I were to take the integral from, doesn't matter what it is, negative 3 to 3. Alright, negative 3 to 3. So I'm going to take the antiderivative, the definite integral from negative 3 to 3 of x squared dx using the first fundamental theorem of calculus. We have x cubed over 3. Then negative 3 to 3. We get 3 cubed over 3 minus negative 3 cubed over 3. And we would get an answer. 3 cubed. 3 times 3 is 9. 3 9s are 27. 27 thirds. This becomes negative, so it's 27 thirds, right? Whoops, I'm sorry. This stays negative. Yeah, negative, very positive. And we get 54 thirds. That is the area between the curve and the x-axis from here to here. Well, there's a property that says if this is an even function, and we're going from opposite values, negative 3 to 3, that we can actually write it like this. I'm going to move this over, if you don't mind. I'm going to move this over. So if it's an even function, there's a property that says f of x dx, the antiderivative from negative a to a, in this case was negative 3 to 3, of f of x dx, only if f of x is even, is equal to 2 times the antiderivative of 0 to a of f of x dx. Ask yourself the question, why is it 2? Well, you might look over here and say, okay, well, it's because of the symmetry, we know that this area between the curve and the x-axis is exactly the same as the area between the curve and the x-axis here. So just to simplify things, we can say from 0 to that x value, we must multiply that area by 2 and we would get the total thing. Okay? This is only true if f of x is an even function. What if f of x is an odd function? And let me move this right over and we'll do x cubed. Actually, you know what? I'm not going to use x cubed. Can you think of another? How about a trig function that's odd? Trig function that's odd. You got it. Sin x it is. So we have sine x. So we know what sine x looks like. Low, middle, high, middle, low, right? And we're going to go this way as well. We know that one period of sine is 2 pi, so we have 2 pi out here, negative 2 pi over here. This is pi. This is negative pi over on the left side. We are going to find the area from, we'll say negative pi over 2. I'm going to make it blue. Negative pi over 2 to pi over 2. So we're going to take the antiderivative from negative pi over 2 to pi over 2 of sine x dx. Using the first fundamental theorem of calculus, you know that the antiderivative of sine x is what? Negative cosine x, and then negative pi over 2 to pi over 2. Now you may already see what this, you might be able to already figure out what this area is going to be, but let's just continue through it. So we get negative cosine of pi over 2 minus negative cosine of negative pi over 2. So what is the cosine of pi over 2? Pi over 2 is up here. It's the x coordinate. It's going to be 0, right? So this is negative 0, and this is also going to be 0. So it doesn't matter. It's 0 and 0. Guess what? It's 0. Why is it 0 if you think from a conceptual standpoint? Because it is an odd function. Odd function. If you look at this area between the curve and the x-axis, it's going to have the same value as this area below the x-axis in the curve. But what do we know about the area that falls below the x-axis? Right you are. This is negative, and this area would be positive. But since it's the exact, has the same numerical value, the negative and the positive would cancel out, or become 0. They had to be 0, I should say, not cancel out. So the property is, if f of x is odd, the antiderivative from negative a to a, meaning the same value is just opposite. It only works when they're the same value but opposite signs. And when f of x is odd, is equal to 0. So keep that in mind. All right. So there's our quick little lesson on even-odd functions and how it relates to definite integrals and some of the properties. John Stone, out.